Welcome to Dr. Nakamura's lecture series on structural dynamics. I am Shunichi Nakamura, Vice President of IABSC and Professor Emeritus of Tokai University. I was educated at Kyoto University for my bachelor and master degrees and Imperial College London for my PhD. I worked for Nippon Steel Corporation as a structural engineer for 21 years. I was engaged in design and construction of bridges, including the Trans-Tokyo Bay Bridge and the Akashi-Kakyo Bridge, this photo, which is the world's longest suspension bridge. After the Akashi Bridge, I moved to Tokai University, where I teach structural analysis, bridge engineering, and structural dynamics. This lecture series of structural dynamics consists of 7 chapters. Chapter 1 through 5 are basic theory of dynamics of structures, such as dynamic equation of structures, formulation of the equation of motion, free vibration, resonance to harmonical loading, and multi-degree of freedom structures. Chapter 6 and 7 are its application: lateral vibration of footbridge and seismic design of bridges. They would be useful to understand how the dynamic theory is applied in the practical problems. This lecture series is useful for students and young engineers who first learn dynamics of structures. You can learn from the basics to application without preliminary knowledge. Chapter 1 Dynamic Equation of Structures 1.1 Introduction to Structural Dynamics. Let me explain what is structural dynamics and why dynamic study is important. Earthquakes, winds, traffic laws are called dynamic forces, which have a characteristic of time varying. Suppose you put a child on a swing. When you push it with 100 Newton statically, it moves, let's say, 10 centimeters. Whereas you push it with 100 Newton rhythmically or dynamically, such as you push it and push it again when it comes back. The swing is getting larger and larger, let's say 20 centimeters, 50 centimeters, even 1 meter. It means the dynamic displacement, called response, can be larger than the static displacement, which creates a dynamic problem. Now you understand why we have to study structural dynamics. 1.2 Basic Equations of Structural Dynamics. Here is a single-story house which is supported by 2 columns. The mass is m and the spring constant k/2 for each. When it is subjected to the external force F, it displaces u. This can be modeled as the single degree of freedom model, SDOF, with 1 mass and 1 spring. There are a couple of ways to express basic equations of structural dynamics. First, Newton's second law, equation of motion, equation 1. U dash is velocity differentiating u by time. U2 dash is acceleration differentiating u twice by time. Please confirm the units. Second, D'Alembert principle. This is the Newton's equation of motion, which is transformed to equation 2, where Fi is called inertia force. This equation 2 is a static equilibrium equation by taking mu2' as the inertia force. Third, Hamilton's principle, which is also called energy method or dynamic minimum work theorem. Equation 3 is the basic equation. T is kinetic energy, V is the strain energy, W is the work done by non-conservative force such as external forces and damping, and delta is a variation. T and V are expressed as functions of generalized displacement Qi, and delta W is assumed as the sum of the generalized force multiplied by the virtual displacement. Then putting them to the basic energy equation and applying the partial integral, we can get this Lagrange's equation of motion, equation 4, which is a useful method for a complicated structure. 1.3 Unit of structural dynamics, which you sometimes confuse. Suppose a man weighs 100 kg. What is the mass and weight? There are two unit systems, imperial unit and SI unit. Imperial unit is an old system, and this man's weight is 100 kg F, and his mass is 10.8 kg F square second per meter. The gravity acceleration g is 9.8 meter per square second, and the weight F is the mass m multiplying by g, F equal mg. SI unit is commonly used for the scientific and engineering field. This man's mass is 100 kg and the weight is mg, which is 100 kg multiplied 9.8 meter per square second equals to 981 Newton. For the dynamic problems, SI unit must be used. Chapter 2 Formulation of Equation of Motion. 2.1 Newton's second law, Equation of Motion. Let me explain how to formulate the dynamic equation using the Newton's second law. Assume the single degree of freedom model SDOF. First, the external force Pt, which is a function of time t. Next, the damping force Fd, which restrains the dynamic movement. When the mass moves to the right, it works to push it back to the left. When the mass moves to the left, it works to pull it back to the right. These are examples of dampers, which consist of the cylinder and the piston. The piston moves up and down in the cylinder where oil is filled. The damping force is created during this piston movement. The damping force Fd is expressed by equation 5. It is proportional to the velocity. C is called the damping coefficient. Restoring force Fs. The spring has a nature to come back to the initial position, which provides the restoring force. When the mass displaces U to the right, the spring creates the restoring force to the left, which is Ku. K is the spring constant. In summary, put all these forces to the basic Newton's second law. The left side F equals P minus Fs minus Fd. Then we get mu2 dash plus cu dash plus ku equal P. This is the equation of motion of SDOF, single degree of freedom model. Next, let me explain how to formulate the dynamic equation using the Lagrange's equation for SDOF. This is the basic equation for SDOF n equal 1. T is the kinetic energy, V is the strain energy, L is the Lagrange function, and Q is the non-conservative forces, which consists of the external force Pt and the damping force minus Cu dash. Put T, V, L, Q to the basic equation 8. The L over du dash and the L over du are obtained like this. Then we get this dynamic equation for SDOF, which is the same as that obtained by the Newton's second law. Next, we study how to formulate the equation of motion for MDOF, multi-degree of freedom systems. Look at this two-story building, which can be described as this 2 degrees of freedom model with 2 masses M1 and M2, 2 springs K1 and K2, and 2 dampers C1 and C2. The displacements of U1 and U2 are from the initial position. In order to formulate the dynamic equations of this 2DOF, it is cut just above M1. For the upper layer, we have the external force P2, the restoring force minus K2 bracket U2 minus U1, and the damping force minus C2 bracket U2 dash minus U1 dash. So the equilibrium of the upper layer is obtained by equation 9. For the lower layer, we have the external force P1, the restoring force minus K1 U1, and the damping force minus C1 U1 dash. In addition, there are reactions from the above layer, plus K2 bracket U2 minus U1 and plus C2 bracket U2 dash minus U1 dash. So the equilibrium of the lower layer is obtained by equation 10. Let us simplify the equation of motion for 2 degrees of freedom structure. They can be transformed like this. Then they can be expressed with a matrix format by equation 11. This is a 2 by 2 matrix. This can be expressed by equation 12 using the mass matrix M, the damping matrix C, the stiffness matrix K, the displacement vector U, and the external force vector P. Please notice that this is exactly the same as that of SDOF. The matrix format is very useful to describe the MDOF dynamic problems. Exercise 1.1. Find equations of motions of 2 degrees of freedom model by Lagrange's method. Answer. First, T, V, Q1 and Q2 are obtained as this. For 2 degrees of freedom model, n is 1 and 2. Then put T, V, Q1 and Q2 into the Lagrange's equation. We have the same equation of motions obtained by the Newton's second law. That's all for this lecture. See you next lecture.